ASA from his books, works for years and years, but I'm a relatively newcomer in ASA's cloud. Since we met physically for the first time a couple of years ago, and then we went visiting in sabbatical in Paris, and then I went visiting ASA in the Technion for a year on sabbatical too. And so I don't know what to add, as people have said now. I don't know ASA since a long time. I don't know, you know him very well and stuff. And so I find myself not know what to say more. And finally, I found that what I can say might be something that you, when you met ASA for the first time, would have feel. And maybe, so the ASA, for me, is the most positive, optimistic person I ever met. When you're more anxious and you meet someone like ASA, it gives you momentum all the time, positive momentum, optimistic momentum. When he went to Paris, he said, oh, let's go to Paris to find a school for the daughter, and let's find a school, he found a school. Then find an apartment, it's not that easy, he finds an apartment. Okay, sometimes you want him like, be careful with the visa, you know, if you go and if you are late, you say, well, there will be no problem. Then there was a problem. He flew back to Israel, he came back, nothing changed, still the same positive momentum all the time. And this is true in life, true in physics, and true for collaborating. And at some point, you get used to it. You get used to this, and you finally don't even notice it. And until the time ASA goes somewhere else, or you left, and then you start missing ASA. So, as a newcomer, I would say that my first feeling with ASA is that ASA is someone that you miss so much, that is not there. And this is why I wish you, in a very selfish way, more, a lot of decades of physics, so we can meet again. So, about physics, my talk will be about bound states in one-dimension systems and how you can describe them by effective theories and get some kind of a general understanding about them. So, in one dimension, bound states are very common. Something like, you know, the amount of attraction in one dimension from bound state. The best example are integrable models like the singular model, or Oslover model, a system like this, where you find exact bound states, I would say, for the problem. In this model, the elementary particle, which is in generality, is already massive. It's a mass particle, and the bound states are higher in area. So it's a very interesting situation. But the situation I want to talk today is the reverse situation, is a situation where the single particles here are gapped, but the bound states of them are massless. So they are the low energy excitation of the problem. And so this is a situation that occurs very frequently in multi-species fermionic system when the spin gap opens. When I mean multi-species, I mean it can be a channel in a wire, it can be a spin, it can be a ladder index, something like that. So when the spin gap opens there, then single particle excitation general are gapped, and you might expect to have eventually bound state of this one massless. So the most well-known examples are two pairs for spin on half, but in cold atoms, a lot of variety of this kind of massless bound state has been found, like trions or quartets, which are essentially three-color SU3 or four-color SU4 bound state on the side, or BCS spherical Cooper pairs with higher spin than 1/2. The Kondo lattice is another example. The recent example we worked out with QCD2 or non-model where you have this kind of bound state. So when these bound states are massless, what you can expect is that there will be some fixed point that is going to describe this, the physics of these guys. And so there are two situations. The first situation, which I will focus mainly in this talk, is when the spin gap opens everywhere in the channel index. So the only massless degrees of freedom is total charge fluctuation, which will be described by the Luttinger liquid universality class that has been proposed in a seminal work by O'Day in the last century. And, but there is a second situation which is much more complex, is when the spin gap opens partially in the spectrum. So you have remaining spin degrees of freedom, which are masses on top of the Luttinger liquid. So then you would have a Luttinger liquid plus some kind of a CFT, and the interplay between the two might not be that simple. This is, for example, what's happening in the so in this talk, I will briefly show you how one can describe this bound state within the framework of the Luttinger liquid universality class. Then I will show that there is some canonical constraint that comes from the nature of this fixed point. Then there will be another set of constraints that will come from the underlying high energy spin degrees of freedom that get gapped. And this will give me some generic bound state. We'll say a word on the mod phases of this. And if I have time to talk about recent work that we are doing with AS and an assessment on the composite fermion with one kind of a bound state. So I'm considering a system of n-Fermionic species which are interacting in a way that's on the end out of the n channel, none of them will be decoupled. If they decouple, then I consider a smaller number of channels. For simplicity, I assume that they have the same density, but only one Fermi vector shared by all these species. So for sufficiently weak interaction, and considering just one channel here, we can use a low energy expansion of the fermions around the two Fermi points, left and right movers. And again, for the work, then you can find an expression of this left and right type of bosonic field, where theta is a charge bosonic field if phi is a current bosonic field. The point here, I don't want to go into that detail, is which is an important point, that the total charge associated with the field is an integer, which is conserved, as well as a current quantum number, which is also conserved. Okay? So, and this is for each of these channels. When you have n channels, and when the gap opens, what's happened, if you look at the low energy physics, okay, small, very low energy, is that an arbitrary excitation, an arbitrary combination of this fermion with the different channels will be gapped in general. And only certain singlet combination of them will survive and will be massless. So there will be some kind of a selection rules on the total charge and the total current that will be associated with the fluctuation of the total charge degree. And these selection rules are is the bound state. So there are many ways to get to this selection rule. Maybe the most simpler and answer is to go to the Luttinger liquid universality class and use a phenomenological organization, which basically tells you that once you have a Luttinger liquid, which is Hamiltonian there, and you have two fields, conjugate field describing the total charge degrees of freedom, and use the Luttinger parameter as well as u. All what you need to go to O'Day paper or German book is to know the density, won't you? And whether it's a boson or a fermion. So if you have a charge, even a charge even, then you have a boson, and if you have all charge bound state, then you have a fermion. And then the density here of this bound state is just the total density divided by the charge. If you suppose that the bound states are local when expressed in terms of the elementary fermion, and this builds up momentum scale, the fermion momentum, and then everything is in river form. All the physical quantity can be expressed in terms of all this quantity. So the important point here is the density expression and the single particle pressure operator for boson and fermion. The important point here that these are expansions in this harmonics of this fundamental state, which is depend only on the density of the number. So in a similar way as the free fermion problem, then there will be a total charge here, which is associated to the charge right here, and the total current for the number. And these are constrained whether you are describing a boson or a fermion. If it is a fermion, that the sum of the difference of the charge and the current is given. And if you have a boson, just you have a constraint on the current quantum number. So that seems to be the end of the story, that what we are looking at the constraint on the physical charge and the physical current when expressing the basis of the original Fermionic thesis. So now the physical charge here, when we express this in the inverse states of the elementary fermion, is just this integer q bar times the charge. So it's quantized in unit of charge. Now the total current has to be quantized in the unit of some new quantum number, which is the quantum of current. And for in the literature universality class, we see that this Fermi momentum is directly related to the density. But in the literature liquid, when you express this in terms of the elementary Fermi quantum numbers, then this momentum is proportional to the original Fermi momentum of each species, and the coefficient of proportionality is the quantum of current. This is only from the relation between current and momentum. If you equate these two equations, then you get this quantum of current as n divided by q, which has to be an integer. And this is a constraint that is fixed by the structure of the literature liquid theory. So you can go into this way and this. Another way to say it is that q and g has to be drawn to the total number of parts. So this is somehow related to some kind of a conversion of the literature theorem here, where from the outset you suppose you have massless degrees of freedom, and you get momentum, massless mode of class in terms of the original K with J is the elementary current from the number. Okay. So downstate, you can see it as a selection group on the charge and current quantum number in the basis of the elementary fermions. So for Q odd, for fermions, here's an example, Q equal 1 and J equal 3. For boson, you have an example with Q equal 2 and J equal 2. Okay. So the point here is that the downstate here can be seen as a degree of confined charge and also a degree of confined current. So just to be more complete here, so here are two examples for Fermionic downstate and bosonic downstate. So for one species, you recover the quantum number of a spinless fermion. And for n equal 2, you have the bosonic state on the spin 1/2 Cooper pair with a charge 2. And these two have preserved momentum, Fermi momentum. For n equal 3, you start to have totally maximally confined charge state with triant and n equal 4 for quartet, which again conserve the momentum. But you start to have also, and grows, new kind of downstate where instead of having a total confined charge, you have a total confined current. So here is an example with a fermion with that charge 1 and a current quantum number 3, which means that this fermion has an enlarged Fermi surface. And here is another example for boson when you have a charge 2 and an enlarged Fermi momentum. So generally, the spectrum of these bound states will start from a maximally confined charge up to maximally confined current for both, for fermion and here for boson. So there might be a lot of solutions, of course, in between them. It's not, you need more information to get the specific bound state. But as I'm going to show you, we can say something about these two extreme maximally confined charge and maximally confined current states. But for this, we have to rely on the nature of the high energy spin dynamics. So this will give you some generic answer. So we have to get some model of the spin sector dynamics. And so make some kind of a hypothesis that we are generic field, so we have spin charge separation, that the total charge will be the same, and that have chiral symmetry and gravity invariant and time reversal, and also that sufficiently decoupling so that I can get an effective action expanded on the right and left field. So the effective Hamiltonian in this case is expected to be the generic full-Fermion interaction here. And I choose to write in terms of the SU and chiral form, but this is a general 4 Fermi interactions. And from that, we might stay there and say, no, nothing can be said more than that, because the interaction can be whatever you want. In fact, there is very important work in almost the last century or so that says to you that even if you are in a gap system, when you go through RG, these couplings here have the tendency to flow at low energy and to find to reach the maximal symmetry that can be reached in the system. It's called dynamical symmetry enlargement. So in such a case, maximal symmetry you can reach here is SUA for any Fermi. And so you can say, okay, now why don't we look at what are these, the bound states that are stabilized at this maximum symmetry. So the point is that there may be also other attractive rays than the SU1 rays with maximum symmetry enlargement. And I'm going to use this slide to explain qualitatively which kind of curve. So here is the typical phased LG diagram of the XXZ model for the 2. And these are two couplings, one in some parallel direction to SUN and the other in the perpendicular direction. So for the points in here, you can have a massless phase when all the coupling are irrelevant. But in the massive phase, you see that for G4 positive, then you have the attractive ray, there is a flow toward that low energy, toward an attractive ray where G parallel is equal to G perpendicular, where there is this energy. The point I want to make is that in general there is also other attractive rays here, which can be obtained by some duality transformations. So the best example here, if you think about the XZ model, is the duality transformation will be changing the sign of G curve. It will be a rotation of pi along the Z direction, but that can be other. And what is very nice in this case for SUN is that we know all the possible dualities here that you can have in for SUN, which are labeled here. So I don't want to enter into detail, but the point I want to make that if you believe that there will be some pocket in Hamiltonian space with the dynamical symmetry enlargement with SUN3, automatically with the same weight in Hamiltonian space, there will be all these duals and effective symmetry and Hamiltonian. So the general strategy to obtain some information on the possible bound states will be to assume that when you have a string gap, to get the low energy sector, you have to project into either a SUN singlet state or this dual SUN singlet state. And we know all about this duality symmetry, and then out of it, we find 5 types of generic bound state with this maximal dynamical symmetry enlargement. So the first one, the baryon variance, in the sense that they are the most natural, looks like the QCD, which are maximally confined charge. So they are the charge n in n species, they have a conserved Fermi momentum. So you have 2 types of them. You have SUN singlets, which are trions quartet, and the typical wave function of this baryon are SUN make on one side. But there is another one, which is dual, in sense to this, where you can make bound state with that, where you make a bound state with a charge P baryon, with a charge n minus P, so the total charge is n. And the bound state has the wave function is in term maximum at some distance, which is inversely proportional to the density. And these 2 states have a maximum charge, the maximum confined charge, they have a charge n, and they have the no unconfined current, so that the Fermi momentum is conserved. The 3 other states are the dual of these states, which are maximally confined current states. So in this case, there are 2 possibilities, whether n is even when you have bosons. For this case, you have charged 2 bound states, and the quantum of current is n over 2, which is maximum realized. And you have either SQN singlet, which are S wave pairing, or S in singlet, who are P wave. So just the P wave pairing is here, it's an S1 state. And so people are not used to SPN. SPN, the SPN matrix here is essentially the Clebsch curve that projects the half-integer speed on the two half-integers. So these are, and this was, and the last one, which states the maximum undefined current, is when n is odd, when you have a charge 1 from you, and the maximum current is of n, which means that you have a fermion which is a very large Fermi surface as compared to the original Fermi surface of the frame. These are S1 single composite fermion. Right? So, okay. So how do we, this is a complicated, but this is very simple. This is really the analog of the composite fermion with the traction on the effect. In the sense that here you have n fermions, you create one fermions, minus 1, and then you dress it into n minus 1 over 2 particular excitation. Right? And these particular excitation are there to give precisely n minus 1 kf to the excitation. So in the composite fermion, the fractional control effect, this state is non-local in terms of the original fermion. But here, because you have n species, this state is completely local in terms of the original space. So it's a local composite fermion. And for n equals 3, you can see even that this state is a fermion, the bound state of a single fermion and a spin 1. Here. So you can write it like this. Okay. So just a quick word on the mode phases. So for fractional downstate fields, you can use, go back to the Thierry's book, and the type of mode phase will be essentially the same as you have for spinless or hardcore. You have convolutional mode insulator with broken translation symmetry, so you just have to replace your favorite fermions for downstate by the spinless fermion or a hardcore boson to get the same kind of thing. What's new here is for integer bound state field, translation symmetry remains unbroken, but you have essentially an integer number of bound state per set, so translation symmetry is unbroken. So for spinless fermion, for example, this is the Pauli insulator, so completely reduced. But here what's counted is the bound state density, which is related to the original density with this current quantum number. So you see that if you have confined current, you can have a state which is completely translational invariant, one bound state per side, without being a Pauli insulator. So here are two examples for the for Bosonic and Fermionic case at the bound state density if you want. So for species density 1.5, then you have essentially one bound state per side. And in the composite fermion here also you have essentially one bound state per side, and the bound state in this case is almost non-regional. So in this case it's either trivial or topological insulator. Okay? So I won't talk about this, but these people have shown that for certain condition of the interaction, this can lead to a topological insulator, which is called a holding topological insulator in the charge sector, as was introduced by Erez, Thierry, and Relatore. And here, we are starting to study this kind of bound state with Erez and Anna, and to show that eventually this will lead to topological insulator. So let me quickly review the effective Hamiltonian for this kind of property found in bound state. So it's just a Harvard model, and with a P-wave pairing term with V negative that wants to favor creation of P-wave pair. So here's the qualitative phase diagram that's located from RG. So for zero P-wave pairing term and U negative, you get triangles, which are these three states, which are SU3, but when the pairing interaction gets sufficiently attractive, then you enter to a new phase, which essentially is given by this composite fermion, okay, which is this spin 1 attached to this fermion. So this is the phase diagram at generic field. So there will be the phase transition between these two states, which essentially is. But let's look about the knot phase here, where we have one of these composite fermion per site and this phase diagram. So either even at v equal to 0, you have the Hubbard model here, for which is the SU3 Hubbard model. And we showed a long time ago that there is a knot transition at 1/3 filling at a critical value of u, which is 2.8. So it's a finite value of u. There is not a knot transition is at a finite value of u, which means that it's separated between a liquid phase to a knot phase. So we can show that this time is likely to continue here for finite v. Okay? So the typical phase diagram of this filling would be to have a knot insulating phase at large u and at small u and large v, negative value u. So you can go here and use straight booking limit, but already from the picture here, you know almost what this is going to be the result. Because for very large u, the charge will be stored on the site. The only remaining fluctuation will be spin fluctuation. We have spin 1, so most likely what you get is the quadratic chain for spin 1. And you can go a little bit more in detail, and you know the phase diagram of this is very well known. And going for V negative, what you get here, you want to know the whole phase. So what is the phase here for the strong cooking is a spin 1 holding chain with spin 1/2 edge, spin 1/2 at the edges. So these composite fermions, when they enter the knot phase, even at least in the large U, they behave as a spin 1. So now the idea that we want to go is okay. So here we have a spin 1 chain, which is logical. But since we have a knot transition here at a finite value of the coupling, there is also a Luttinger liquid phase. And the question is, what is the nature of this Luttinger liquid? So one thing that you can do is go to u equals 0 and go to check what is happening on this. So this is first work in progress. But you can do a mean field approximation of the pairing term here, and with another surprise, what you will take is essentially equilibrium chain, which are coupled with the approximation that the delta I is the same line of translation by a common phase. So in the mean field approximation, which is phi equals 0 and for suitable value of the chemical potential, what you get is 3 Majorana mode of the light phase. Okay? Out of which you can look at the degeneracy here by looking at the fermion which is shared by this two-edge Majorana fermion. You obtain 2 power of even fermion parity or odd fermion parity for the vacuum, but creating pairs, pairs of 1, 2, which is a spin 1 chain, spin 1 object, and also in the other sector the same. So what happened beyond the field? That you have to restore particle number conservation, and for this, the phase fluctuation will lift the even more degeneracy as we can in this similar work, and then we expect at the end to have half of these 8 states at phi equals 0, and to get only one given parity sector of the state. And since a pair of Majorana is neutral under parity, what we expect to have is still one spin 1/2 at each edge here in this value. This is just a hand-waving argument, but it's reasonable to think that this is what is going to happen. The important point here that these edge states are protected by the SO3 symmetry. So if you compare the situation with wires and channeling the wire, won't have this kind of a symmetry you expect from the worker that this edge state will eventually get gap, but with this SO3 symmetry, so conclude. So for this composite fermion, it is much likely that H might survive the knot condition and it is either in the knot phase and the liquid that this has to be checked. And the natural question here is whether this person survives integration.
Let's thank you again.